Morning, PreCalc kids. Today we're going to put all that trig knowledge to test as we look at graphing with polar coordinates. Notes out and away we go. So we're looking at graphing using polar coordinates. What are polar coordinates? A polar coordinate system is a process of recording the position of an object. We're going to use points to start, using the distance from a fixed point and an angle. So instead of using a rectangular Cartesian system, we're using a circle. We're going to call the pole the center point of our graph, or the origin of a polar coordinate system. It's not really an origin because origin is for the Cartesian system, but it's going to act like an origin. We're going to call the polar axis a horizontal ray directed to the right from the pole. That's going to be our initial side of our angle that we looked at in trig. We're going to call polar coordinates any ordered pair in the form r theta, where r is the distance from the pole to the point. So that's going to give us our length away from the point. And then theta is going to give us our location, the angle from the polar axis to the point in degrees or radians. Now I'm going to show you the picture. This is what our graphs are going to look like. And we actually have polar graph paper. Remind me in class, and we'll get some of this out. If radius is positive, so if r is bigger than 0, then theta is the measure of any angle from standard position to the terminal side, just like we did in trig. So here's our r, distance away from the origin, and then theta gives us the location on the circle. But r can be negative. If r is less than 0, negative, positive, then theta is the measure of any angle from standard position to the opposite terminal side. And so actually what we're going to see, if r is negative, it's going to result in a flip. We'll see how that works. For example, let's graph each point. So number one, we want to graph the point 360. So first we'll look at our theta 60. We'll find 60 degrees. And 60 degrees is, can't hardly read that, right here. So here's 60 degrees. So there's our angle. So from our initial side here, we're coming up 60 degrees. And then we want to be 3 units out. And so here's the center. Here's radius 1, radius 2, and radius 3. So there's our ordered pair, 3, 60 degrees. What about negative 1.5 and 7 pi 6? So now we're on radian graph paper. Well, here's 7 pi 6. So we're going to follow that around to be 7 pi 6. But then our radius is negative. So instead of coming out this way, 1.5, this causes a flip. So if we look at where positive 1.5, that would be there. But because our radius is negative, we're going to flip to the other side, right? This is also the supplement. If we think back to geometry, so 2 pi minus 7 pi 6, that puts us back at pi 6. Sorry, not 2 pi, pi is 180. That puts us back at pi 6. So we're on pi 6 at 1.5. So there's our point, negative 1.5, 7 pi 6. Remember, if theta is greater than 0, theta is measured counterclockwise from the polar axis. If theta is less than 0, we go counterclockwise. All right, so here's our circle. So here is positive theta, and then here is negative theta. So we call that from trig. Next up, let's graph the point negative 2, negative 135. So one way you can think about this is we can just go backwards, counterclockwise, negative 135. And where does that take us? Well, that takes us to 360 minus 135, and that takes us to 225. So we are on 225, which is halfway between 220 and 230. So there's 225. and we're at -2. So again, from our initial side, we're going to come all the way over to 2. Put a dash line there for that. And we're 2 out, which is actually really close in. And so we're actually going to be about right there. So there's our point. Again, the negative radius flips it back to the other side. So really we're back to -180, which is back to whatever that is, 45. What other ordered pairs would give the same point? So it turns out for any ordered pair in a polar graph, there are others as well. So we could, this was the negative version, right? So we have a negative version, which was this one. We have a positive version. What would that be? Well, that's a +2. And then what's that angle? Well, that angle was 45 degrees. We can do a positive radius and a negative angle. That's a 2. How do we get to the same 45? Well, that's going the other direction, and that's going to be a -315. And then we can do a negative radius and a positive angle. How are we going to do that? Well, our positive angle, well, let's go with our negative radius. That's -2. So we're over here, right? There's our point at 2. Negative flips us back here. What positive angle is going to take us back there? That's our 225. And then again, there's our negative was our original point, -2, -135. So again, there's 4 ways to describe any ordered pair. So here's our notes on that. Multiple representations of r and theta. If any point P has a polar coordinates r theta, P can also be represented by polar coordinates r theta plus 2 pi k, or -r theta plus 2k plus 1 times pi, where k is any integer. So we're just going up by integer 180 degrees each time, or pi each time. Number 3, name 4 different pairs of polar coordinates that represent point S on the graph with restrictions. We want to keep theta between +360 and -360. So first, what is the point we're graphing? Well, notice this is 1, 2, and 3 units out. And also notice this is in degrees, and we're at 150. So what are the other 3 points we can get? Well, instead of going +150, we can go negative, the counterclockwise direction. And that's 360 minus 150, and that is -210. We can also flip that point. So instead of being at +3, we can be at -3. So there's our -3. There's our +3. How are we getting to this point with a -3? Well, again, we can use a positive theta. Positive theta is going to take us almost all the way around the circle. So that is 150 plus 180, because we're going 180 degrees around, and that is 330. And we can also do a -r and a negative theta. That's going backwards 30 degrees, which is -30. So again, given any point, we can find 3 other ways to describe that point. We can also define a polar equation. A polar equation is an equation expressed in terms of polar coordinates. A polar graph then is the set of all points whose coordinates are theta satisfy a polar equation. It's kind of like graphing lines, but now we're switching to polar graphs. What do our lines look like in a polar graph? Well, they get kind of interesting. We have 2 basic polar equations, and they have the form r equals k and theta equals k times pi. And let's see what those look like. So graph each polar equation. So what's one way we can think about this? Well, if r is 3, we want, again, all the points that are r theta. Well, we know r has to always be 3, but theta can be any value. We can think about a table of values if you want to think about it that way. But basically, where is the radius always going to be 3? So if we start at 0, there's 0, 3. If we go to 90, there's 0, 3. If If we go to 180, there's 3 and 90. If we go to 270, there is, I get these all in the right spot. I did not. That goes there. And there's 3 there. And what do we get? Well, if we graph all of those points, we get a circle. So any equation of the form k theta, we get a circle, where k is some number. What about where theta is 3 pi halves? 3 pi 4, sorry, 3 pi fourths. Well, now we can use any r with the theta 3 pi fourths. All right, so what are we looking at? Well, we could have 1 and 3 pi fourths. 1 and 3 pi fourths would be there. 2 and 3 pi fourths would be there. 3 pi fourths. 4 3 pi fourths. But we can also have a negative r as well. So -1 at 3 pi fourths, -2, -3, etc. And what do we get? All the points in between, we get a line. So giving a variable r with a theta, we're always going to get a line on a polar graph. So those are 2 basic graphs, the circle and the line. And one more, graph each polar equation. Go ahead and pause the video. Go ahead and graph these and then come back and see if you can do it correctly. All right, we want r of -2. One thing we can do with this, kind of the smallness of the circle, is we can actually go by increments here. So if I actually call, I don't know, maybe every 4, 2 or something, 1, 2, 3, 4. So I'm going to call that 1, 1, 2, 3, 4, and call that 2. Again, we can set increments on a graph just like a coordinate plane. We want everywhere the radius is -2. Actually, -2 would have been over here on the other side. Doesn't matter. This is our circle equation. We want everywhere where the radius is going to be 2, which includes the positive radius, and so there's our circle. Letter B, where theta is 3 pi fourths, 3/4 pi, sorry. 3/4 is, again, right here. That's going to be our line. And there's our lesson. Homework is 16 through 40 evens. Remind me in class to get graphing paper, polar graphing paper. See you kids in class. Talk to you later. Have a good day.